Good day. I'm Norman Wahlberger. In the last few videos we've been talking about some of the disadvantages of using angles as a framework for geometry and trigonometry. One of the important aspects of this is that if you try to use angles, then you are necessarily forced, whether you like it or not, to consider the circular transcendental functions. The functions sine theta, cosine theta, tan theta, and the more complicated ones cotan, cosecant, and secant. These functions are naturally associated to the geometry of a circle, but because we are introducing a circle or circular arcs to measure angles, they naturally appear. And despite what some people will try to convince you that these are relatively easy functions, they are in fact quite complicated. And they and their inverse functions present a major challenge for young people and educators trying to teach young people geometry. When we first start learning angles in public school, we're made to think that it's very simple because of the linear aspect of angles. If you have one angle of 25 and another angle of 28, then we're taught that we can add those angles to get 53. There's almost always a picture like this associated to a question like this, because there's a slight ambiguity if the picture is not there. If the picture is not there, then you could easily make the mistake of thinking, well, you might have an angle BAC like this of 25, but then maybe the angle CAD is like this, CAD down here. If that was the picture you had in mind, then you would be more inclined to take the difference between these angles as the resulting answer. So if you just know two angles, knowing the combined angle is really a situation where there's two possibilities. So that's one way in which angles appear simple but are rather deceptive. When these young people are being taught this subject, they're often given many questions like this. Here's a quadrilateral and you have three of the angles, and we will want to know the fourth angle. It's not too hard because the four angles sum up to 2 pi. Assuming you have appropriate convexity and you have a picture that represents the angles correctly. This kind of question involving angle chasing gives students confidence, but it's often a misplaced confidence because out in the real world of applications, engineering, surveying, and so on, this kind of angle chasing is usually not the core problem. Most of the really difficult aspects of dealing with angles, in fact, relate to a diagram like this, where you have a right triangle with, say, side lengths A, B, and C, and one of these angles, say that one there, is theta. And the important thing is that there's a relationship between the angle and any one of the ratios that you can obtain by looking at these three quantities. So B over C, this ratio here, is connected in some way to theta. If you know theta, then you know this ratio, and if you know this ratio, then you know theta. But the connection is a highly non-obvious connection, and it's these days given by this function sine theta, which is usually defined in this way. The ratio A over C is called the cosine of theta, and B over A is called the tan of theta. So in the modern setting, these three things are not so much ratios, but functions that take an input theta and output the ratio. These definitions are only valid when we have a legitimate right triangle here, when the angle theta is less than pi over 2, 1.570. Equality is all right for these ones, however we need strict equality for this one, otherwise the A being 0 will confuse things. So a natural question is, what happens for bigger values of theta? And here most high school students have another big conceptual jump to make as we go from right triangles that look like this to the geometry of a circle. So after students learn first the ratio definition of the cosine and sine and tan, they then move to the circular definition, where we think of a point P on the unit circle, and that point P is associated to it an x and a y coordinate. Now these are no longer distances, they are coordinates, and there's a big difference between coordinates and distances because the coordinate is changing in a nice way as you move along here, while distance is not. Coordinates can become negative, while distance is always positive. But it's the actual coordinates that are involved now, so we've made a conceptual change from distance to coordinates. And this coordinate x is called now the cosine of the angle, and the y is called the sine of the angle. And that's valid for arbitrary angles, even up to 360 or 2 pi. Unfortunately, this definition makes it very hard to calculate this function if you're actually given concrete values. And it's only later in calculus, after a few years of calculus, that students learn that there are series for these functions. Unfortunately, the development of these series and the definitions are often not really done very well in most undergraduate treatments of calculus, which often rely on high school definitions of these functions instead of giving very precise mathematical ones. This is a problem that was recognized by the great English mathematician G.H. Hardy about 100 years ago, who pointed out very clearly that there was a serious logical gap in most treatments of calculus having to do with these functions. Unfortunately, it seems that most modern textbook writers haven't studied Hardy, and so the confusion in the definition, the proper definition of these trigonometric functions is still with us today. Nevertheless, the students learn to draw these functions in a way, and they learn lots of special values having to do with the 2 triangles that they particularly love in ordinary geometry, the 90-60-30 triangle and the 90-45-45 triangle. These are pretty well the only 2 triangles that modern trigonometry gives students the tools to deal with without a calculator. So it's all very complicated, and there's a lot of logical difficulties that are usually rolled under the carpet in treatments of calculus books when it comes to these trigonometric or circular functions. Next time, we're going to have a look at an even more serious difficulty with modern mathematics. This is a very serious problem that's going to have ramifications throughout this series. We're going to talk about functions, what exactly a function is, what it should be, and the right way of thinking about it, and also some of the serious weaknesses with the current way of thinking about functions. I hope you'll join me for that. I'm Norman Walbacher. Thanks for listening.